Hello everyone, and thank you for joining today's webinar, Lignin-Based Polymers. A little bit of information about MDPI. MDPI is a pioneer in scholarly open access publishing and is supporting communities since 1996. It is based in Basel, in Switzerland, and has the mission to foster open scientific exchange in all forms across all disciplines. We have 478 open access journals, including 469 peer-reviewed journals and 9 conference journals, supported by more than 295,000 academic experts who share our mission, values, and commitment to providing high-quality services for our authors. Polymers is an international peer-reviewed open access journal on polymer science, which is published semi-monthly online by MDPI. It provides interdisciplinary forum for publishing papers related to polymerization methods, theory and simulation and modeling, understanding of new physical phenomena, advances in characterization techniques, and harnessing of self-assembly and biological strategies for producing complex multifunctional structures. Regarding today's program, we will start the presentation with an introduction from the chair, followed by the first presentation on lignin for formaldehyde-free resin applications. The second presentation will be on lignin-based polyurethane coatings for sustainable paper packaging. And the third presentation will be on synthesis of lignin polystyrene copolymers from forest residues, a case study with ponderosa pine. At the end, we will have a Q&A session. If you are interested in knowing more about the special issue related to this webinar, lignin-based polymers, where the deadline for manuscript submission is 20 December 2025, please follow the QR to go to the website of the special issue. As I've mentioned, at the end, we will have a Q&A session, and please use the Q&A box, which is at the bottom of your screen, to add your questions. And don't forget to add the name of the person you are addressing the question to. Now, I will let our chairman start the webinar. Please.
Good morning, everyone. I'm happy that you found some time to join us for this webinar on lignin-based polymers. I will start with a little bit of introduction on lignin as important biorenewable resource as an alternative for current polymers, and then I will introduce our speakers, and we will go and talk a little bit more about specific area of research they are involved in, and at the end, as our speakers at the very beginning, moderator said, we will have Q&A session. Lignin is very abundant natural aromatic polymer. 300 billion tons of lignin are available on Earth. However, only about 70 million tons of lignin is extracted annually from lignocellulosic biomass, mostly through kraft pulp technology. But only 2% of lignin is used in different formulations, the rest being combusted in kraft recovery technology for power and energy. Lignin is still a mystery. For that reason, we are trying to isolate lignin in its native form from lignocellulosic biomass. And we see here mildwood lignin, showing that lignin in its natural form is actually light colored. After processing with chemicals at high temperature, it gets modified, converted into very condensed form, which is seen here in kraft lignin, which is dark colored. Again, lignin is mostly combusted for the reason of its high condensation. For that reason, we are making some efforts. Research is going into direction of isolating lignin in more natural form, which would be more appropriate for higher value application. And here we see organosolv lignin isolated at forest products lab, showing some improvements, at least in color, which is normally industrial a kind of a flow from industrial point of view, dark color. Today, kraft lignin is recovered in case of mills which recovery boiler bottleneck, and we see the main producers of kraft lignin, Ingevity. LignoBoost is technology developed by Valmet, which is now built in different continents in Europe, in United States, in North America and South America. LignoForce and LignoBoost are similar to each other. LignoForce has an oxidation step before precipitation. It is developed by FP Innovations in Canada. This is a source of lignin which is being investigated by different research centers in the world for to find the ways how we can use lignin in higher value application to add value into the existing kraft pulp technology. Lignin by itself has intrinsic properties which can add to preservation of polymers in regard to its biodegradation, photoxidation, oxidative stress, and in case when we are blending lignin in its pure form or after a certain type of functionalization, we can improve polymers in their natural disadvantageous properties such as absorption of UV light, where they start a chain of oxidation. Lignin can do that for them, and lignin shows competitive to some natural agents, UV absorption agents such as ferulic acid, quercetin, and certainly can serve a role of chemical synthetic UV absorbers to take a role in sunscreens, for example. We show here only at 1% lignin added to PLA, capacity of PLA to improve to absorb UV light improves 20 times. You see on this slide, the different lignins can improve UV absorption different ways. Kraft lignin softwood is very powerful UV absorption agent. Also, when it comes to chain of the radical reactions, lignin is a natural radical quencher which competes well with quercetin and ferulic acid and is way better radical quenching agent than synthetic BHT. So we could consider lignin as a good antioxidizing agent when it comes to stopping reaction, radical chain initiated reactions in degradation of polymers. And also lignin has shown some antimicrobial activities. Here on Staphylococcus aureus, we see those white halos, which means that microorganism stopped growing, and lignin shows again different antimicrobial activity depending on the type. But in addition to blending lignin with polymers, lignin can be used after functionalization either individually or in combination with other polymers as an alternative to current conventional synthetic polymers. And that is what we will hear today from our three speakers who are diligently working on trying to find the best, the most efficient ways in using lignin either craft or some novel lignins like organosolv for these applications. First, we will hear from Dr. Prajakta Dongre on her work on lignin for formaldehyde-free resin application. She is a postdoctoral at Wisconsin Energy Institute at University of Wisconsin-Madison, while she holds PhD from the Department of Chemical Engineering in Syracuse, New York, SUNY SF. She specializes in lignin valorization through bio-based polymer development. She has developed phenol and formaldehyde-free lignin-based resins. That is very important to highlight that most of the conventional work is on replacing phenol by lignin, but in this case, she is replacing both lignin and formaldehyde for green, practically adhesive. In her current work, she is working on oxidative depolymerization strategies to produce higher value chemicals from lignin. That will be our first speaker. Our second speaker will be Dr. Julia Figueiredo. She is ready to present her work on lignin-based polyurethane coatings for sustainable paper packaging. She holds MS in forestry science from Federal University of Icosa and PhD in environmental and forestry sciences from Federal Rural University of Rio de Janeiro, Brazil. During her PhD research, she joined SUNY SF Lignin Cellulosic Biorefinery Laboratory in collaboration with Paper Packaging and Beyond to work on developing lignin-based polyurethanes for paper packaging applications. She is an expert in biomass characterization, pulping, craft and chemi-mechanical, and bleaching, total chlorine-free and elementally chlorine-free. And we will conclude our presentation with the novel work of our speaker, Gia Raju, who will be talking about synthesis of lignin polystyrene copolymer from forest residues, very important aspect of the work of Forest Products Lab to find the appropriate ways to use forest residues coming from forest management restoration projects, in this case on the west case of Ponderosa pine. Gia is a third-year PhD candidate in chemical engineering at SUNY SF, has a very fruitful publication record. You can go to Google Scholar. Her research focuses on the sustainable valorization of lignocellulosic biomass, particularly lignin, through innovative pre-treatment and fractionation strategies. And in her work, she is following principles of green chemistry, trying to develop new solvents for efficient lignin extractions. But in this work, she will talk about lignin valorization in polymerization with styrene to make alternative for styrene in polystyrene application. Thank you, and we will start with our first speaker, Prajakta Dongre.
Thank you very much for the introduction, Dr. Bojanovic, and thank you, Ana Maria, for giving me this opportunity to give this talk. And I would like to welcome everyone to the webinar. And so today, like Dr. Bojanovic said, I'll be talking about lignin-based formaldehyde-free resins. It should be phenol and formaldehyde-free resins. This is primarily my PhD thesis work that I did at SUNY ESF. I will not spend too much time on my introduction since Dr. Bojanovic already introduced me. But currently I'm working at the Wisconsin Energy Institute, working on aerobic alkaline lignin depolymerization. And my PhD is from SUNY ESF with Dr. Bojanovic as my advisor. So as we all are aware that the impact of commodity products, especially petroleum-based products, has not gone unnoticed, and there is a drive to find suitable, sustainable alternatives that can replace some of these commodity products that have negative impact on the climate. The idea is to use sustainable feedstocks such as wood, biomass to offset carbon emissions. So you are not removing carbon from beneath the ground, but you are recycling carbon up from above the earth. And several pretreatment methods are being explored to take advantage of the three major components of wood, cellulose, hemicellulose, and lignin, and it is necessary that all three components are completely valorized. The specific commercial product or commodity product that I'm focusing on are the phenol formaldehyde resins, which are ubiquitously used in various applications, such as in plywood and particle board furniture as wood adhesives, as well as binders in other lamination type applications, or even friction paper, which I will get into a little bit later. Now, the reason to find alternatives for this particular PF resin or PF resin is that formaldehyde has been classified as a carcinogen by the EPA, and phenol is derived from petrochemical sources. So we propose the use of lignin to replace phenol, as it is the most abundant aromatic polymer on Earth, and replacing formaldehyde with furfural. So as Dr. B was saying, a lot of the research in literature is on lignin phenol formaldehyde resins, where partially some portion of the phenol is replaced by lignin, and you have lignin phenol formaldehyde resins, or you have lignin that is modified via various methods and then used to make the resins. However, the work that I did as a part of my thesis was to use lignin unmodified as is, and then cross-link it with furfural and to make your lignin furfural resins, which is also referred to as the catch-all pathway. So you're just you're not purifying or fractionating or modifying lignin anyway. You're just taking the lignin as is and producing materials from it. So just briefly about lignin. Lignin is a 3D amorphous polymer, which is mainly composed of phenylpropanide units. It is linked by carbon-carbon and carbon-oxygen-carbon bonds. There are three different types of lignins that you see in nature, depending upon the species, which differ in the monolignals, which themselves differ in the methoxy substitution at the 3,5 position. As you can see here, so H, G, and S. It ranges from about 15 to 30% of the biomass, again, depending on the species. Softwood lignin only contains G lignin. Hardwood contains SG lignin, S and G lignin. And grasses and agricultural residues contain HG S lignin. So moving to the lignin that we use for making our resins, we isolated lignin from hot water extraction. Now, it is important to note that the hot water extraction process primarily targets hemicelluloses, and lignin is removed as a byproduct. And since it is important that for the biorefinery to become economically feasible, all three components should be valorized, we decided to take the lignin byproduct from this process to make the resins. The lignin that was produced was from three species: sugar maple, willow, and miscanthus. This is what I will be talking about. We did extract lignin from other species as well. The biomass undergoes a hot water extraction at 160 degrees for 2 hours. The extract is then acidified to pH 2, and the lignin is precipitated. And the precipitated is then freeze-dried or oven-dried and collected, which is then used to make the resins. All these experiments were conducted at pilot scale in a 65 cubic feet digester, and the loading of the biomass was about 100 to 250 kilograms. The water to biomass ratio was 8:1, and the size of the biomass differed to whether it was miscanthus, which is a grass, versus wood chips of sugar, maple, and willow. So the concept behind making the lignin furfural resins was as follows. The lignin that is isolated from the hot water extraction process contains some sugars. The idea was to make the resins in acid conditions, which would break down the xylose present in the lignin to furfural, and also cause some lignin-lignin condensation, as you can see here in the diagram. and form either a lignin-lignin condensation product or a lignin-lignin furfural condensation product. So the furfural would act as a cross-linker to bind the lignin molecules. And therefore, creating the adhesive system of lignin and furfural, as you can see from this diagram. So we were expecting that there would be in situ furfural present in the lignin that would act as the cross-linker. However, so before I go into the synthesis method, this is the lignin characterization of the different lignins that were produced from the hot water extraction process. As you can see, most of them are 80 to 90%, so they're relatively pure, with about 5-6%, or 3 to 5% sugars, with xylan being the primary sugar present. So we were expecting that this would break down to furfural in acid conditions when you made the resin. Sorry. So this slide shows the synthesis method of how the resin was made. So we took the lignin from the hot water extraction process and subjected it to acid hydrolysis at 90 degrees C for about an hour. The pH ranged from 0.65 to 1. And if at pH 6.65, there was no furfural added. However, at pH 1, furfural was added. So we tested the effect of the in situ furfural that would be present versus adding furfural ex situ or externally. Once the synthesis was complete, the product was then filtered and dried. And then initial testing was performed using glass fiber strips. So the resin was dissolved in acetone water, and inert glass fiber strips were immersed in this solution of acetone water resin, and then hydraulically cured under high pressure and temperature, and then tested under tensile load. This was to sort of screen our initial candidates to see if we were able to produce mechanical properties that were comparable to the commercial phenol formaldehyde resin. And glass fiber strips were particularly chosen because they are inert, and that was expected there would be no interaction between the glass fibers and the resin. So the strength that we would observe from here is that of the resin alone. We also characterized the lignin for several other of its properties. One of the key properties of lignin is the free phenolic hydroxyl groups, which determine the reactivity of the lignin. And as you can see that all three lignins showcase a similar free phenolic hydroxyl group content, about 2 millimole PHOH per gram of lignin. This is slightly higher than what you would see in literature based on Millwood lignin values, where the lignin is much more preserved, whereas in the hot water extracted lignin, you're seeing some degradation that occurs during the extraction process. The SG ratio also is a key property of hardwood and grass lignin. The more S lignin would suggest that there are more sites for condensation at the S26, whereas if there is more G present, then you'd have the G5 that would open up for condensation as well. And it was expected that if the polymer had more condensation sites, it would be more cross-linked and it would help with the mechanical properties, as is the case for PF resin, which is heavily cross-linked once it goes through its synthesis process. Then we also looked at the molecular weight distribution of the lignins and the resin. As you can see from the table, generally the weight average molecular weight of the lignins alone range from about 2,000 Dalton to 4,000 Dalton, and of the resins increased to about 8,000, 9,000, in some cases 6,000, which indicated to us that the synthesis was successful, that the polymerization between the lignin had indeed occurred, and that we had successfully synthesized the resin from our lignin raw material. This is just to let you know the different conditions we varied during our synthesis was the furfural content, the pH, as I mentioned earlier in the synthesis method slide. Here I am showing you the tensile strength results of the glass fiber studies. And our initial preliminary screening showed that the resins that we prepared, many of them were quite comparable to the commercial Novolac resin. So phenol formaldehyde resins can be of two types. One is a Novolac, which is produced in the acid conditions, and one is a Rizal type, which is produced in alkaline conditions. So since we synthesized our resins in the acid conditions, they were more similar to the Novolac type phenol formaldehyde than the Rizal type. The Novolac type in the commercial process for Novolac type synthesis also requires another crosslinker, HMTA, which I will talk about later in the slides. So as you can see, the initial data showed that many of the lignins, depending upon the furfural content and the pH conditions that it was exposed to, was quite comparable to the commercial Novolac resin. And some of the data also suggested that if there was excessive cross-linking, which meant the molecular weight had gone up, the molecule was rigid. And so if the molecular weight was too high, that didn't necessarily mean that the tensile strength would be high. So it would make the resin more brittle, and it would suffer in the mechanical properties. So there is a balance that has to be struck between, yes, you want obviously for the resin to polymerize, but you don't want to polymerize so much that there is no steric hindrance, and the polymer chain cannot rotate, that it just breaks upon impact. However, this trend was not observed through all the species, but generally speaking, that is what we observed initially. So because lignin will often undergo polymerization and depolymerization reactions simultaneously, so depending on the conditions of synthesis, one or the other would dominate. And that would then determine how cross-linked your resin would be, further indicating how strong or weak it would perform in the mechanical testing. So once we had an idea of that our resins were actually performing quite well with the commercial Novolac resins, we decided to test out some other applications. So the first application that we tested was the Richlite composite, which is a commercial product. The idea behind this is that they used craft paper from the paper industry. Several layers of the craft paper are immersed in Novolac resin, and then they are cured at high temperature and pressure. And then you get a solid, stable sheet of material, as you can see in this picture, which can be used in several applications such as countertops, furniture, musical instruments. So we decided to check if our commercial resin would be suitable for such an application, and how it would compare in terms of mechanical properties. So I started with hardwood craft paper, so similar to the glass fiber strips. Hardwood craft paper was cut into strips, immersed in the resin acetone water solution, and then subjected to tensile testing. As you can see, that we tested it with the HMTA, which is the commercial resin that is used in Novolac synthesis as well. So we tested it with the HMTA crosslinker and without it. And it showed that some resins would perform much better than the Novolac resin without the HMTA, but other resins would require the HMTA crosslinker to give significantly improved strength. So I think this depends on the starting material. from the molecular weight distribution graph that I showed earlier, I can go back for reference, but the miscanthus lignin resin was of much lower molecular weight than the willow resin molecular weight. And so adding of the HMTA benefited it and it improved in strength, whereas the willow was already quite cross-linked in the initial synthesis process, that adding HMTA may have cross-linked it further, but that, it caused a decrease in the mechanical strength because of the steric hindrance or the inability for the polymer chain to move very easily. And so the material was much more brittle and broke under much lower, failed under a lower load. Once we had tested our resins on the hardwood kraft paper and showed, although this was only one layer of paper, we were not able to test multiple layers of paper for this application to truly determine the performance in a real setting. So this was more just to show that the resin did work well even with kraft paper, where you would expect some interaction between the paper and the resin, which was not the case for the glass fiber and the resin. So then we looked into a second application. Novolac resins are also used in friction paper brake parts or automotive brake parts as a binder. However, the key difference here in automotive brake parts is that they're exposed to extremely high temperatures when you're driving your car. And these binders maintain the brake pads, the structural integrity of the brake pads and under mechanical and chemical thermal stresses. So therefore, it's necessary that the resin that you use or the binder that you use is extremely stable under these very harsh conditions. And phenol formaldehyde has excellent thermal stability under mechanical and chemical stresses. This was in consultation with a company called Borg-Warner Incorporation. So they proposed to us that we do two tests. One is the heat age tensile tests, where the resin was exposed to 150 degrees C for 22 hours before testing it for mechanical strength. And the second test was the hot oil exposure test, where the kraft paper strips were dipped in automatic transmission fluid and then exposed to 110 degrees C for 22 hours. So this was to see whether our resins would perform well under the more real world application conditions. However, this was not the case. This is before the heat age test. As you can see, the miscanthus resin shows much higher tensile strength than your PF resin. However, after it's exposed to the temperature, 150 degrees at 22 hours, the strength decreases significantly. That is not the case for PF. The PF very much maintains its strength, which gives it the advantage that it is so commonly used. Versus in hot oil exposure test, similar results are seen. The miscanthus resin significantly drops strength after it's exposed to the automatic transmission fluid at temperature and time, whereas PF also drops slightly, but it maintains 70%, 77% of its strength essentially. So this told us that our resin was not thermally very stable. From our TGA data, we have seen that the degradation is between 300 to 350 degrees for most of the resins. However, when exposed to high temperatures at long periods of time, the resin cannot sustain, and it will lose its mechanical strength over time under these conditions. And so what the conclusion for us was that the resins were more applicable to conditions where maybe more, room temperature conditions, such as the rich light application that I talked about earlier, whereas it will not be suitable for the very harsh condition applications. So overall, my conclusions are that higher molecular weight of the resin corresponded to lower tensile strength because of extensive cross-linking. Lignins from the hot water extracted process demonstrate good mechanical properties, sometimes even better mechanical properties when reinforced with craft paper or even with glass fiber studies. And the SG ratio and PHOH content are significant in demonstrating, significant in determining how your resin would perform. So lignins with high SG ratio and high PHOH content are ideal, and relatively low molecular weight are ideal for resin preparation. And overall, sugar maple and miscanthus lignins are better raw materials. And the reason being is that both of these had high SG ratio and high PHOH. So this is my bibliography, and I think we are taking questions later.
Sure, questions will be later. Thank you, Dr. Dongren. Dr. Figueiredo.
Okay. First, I want to thank you. It's an honor to me to have been invited to present part of my research I developed during my PhD. And this work was developed in a partnership with Laboratório de Biorefinaria Lignocelulose at Federal University of Rio de Janeiro and Paper Package and Beyond Group at SUNY ESF. And the aim of the study was to develop a lignin-based coating for packaging applications. So throughout the presentation, I will talk a little about the packaging industry scenario, the motivation behind this work, our experimental methodology, and the results obtained and our main conclusions. So when we think about the packaging industry, we see that it's a continuously growing sector with this market already valued in $1 trillion. And not only this industry has only this economic importance, but when we think about packaging, we think about the products inside this. And the package allows the products better, a higher shelf life, ensuring products are safe, fresh, and intact to use after after you take off the package. But when we see the most packaging produced are from non-renewable resources. So that's it's a problem. It's the major challenge for the packaging industry. So when we see the many packages produced, we see plastics is the most produced, but I don't remember now, but probably the fourth most produced is paper packaging. But this paper package has the problem that the fibers, because of the structure of the paper, we have the penetration of some fluids depending on the application we have. So we cannot use the paper packaging for all things, for all products. So to develop the properties, the barrier properties of the paper, we can use coatings that will provide water resistance, water vapor barrier, oil and grease resistance, and gas barrier. And we have this today, but although most current coatings are still petroleum derived, several students have explored natural polymers and their derivatives as sustainable alternatives. So among the most investigated are starch, cellulose derivatives, chitosan, lignin, and they have demonstrated potential to enhance the barrier properties while maintaining the biocompatibility with paper substrates And since they are materials that are derived from natural resources, it turns the packaging more sustainable. And the combination of paper with biopolymers increases this biodegradability, improves the recyclability, and the use of renewable raw material. And all of this are aligned with the Sustainable Development Goals, and especially the 9, 12, and 13. And it leads to reduce the environmental impacts. In this contest, our objective was to develop a lignin-based polyurethane using lignin as a polyol, gamma-valerolactone as a solvent, and Dabico as a catalyst, and hexamethylene isocyanate as an isocyanate source to cover the paper and have this barrier properties, maintaining the mechanical strength. That is one of the most difficult things when you think about the mechanical properties of plastics and the mechanical properties of paper. So just to be in the same page, the polyurethane formation occurs via polyaddition reaction between isocyanate group and hydroxyl group, forming urethane linkage. So we need a source of the hydroxyl group and a source of isocyanate group. In our study, we used lignin due to its evidence, as Dr. Projected said, lignin can be recovered and use it. The process that our lignin was recovered was via lignoboost, and it's a low cost and it's compatible with green solvents. And we choose the hexamethylene diisocyanate, HDI, for its widespread use in coatings, offering durability, resistance, and especially for non-toxic amine producer under degradation. And to improve the lignin reactivity, the lignin was solubilized in GVL, gamma-valerolactone, that is a biomass derived, has low toxicity, and it's biodegradable. And to improve the reaction to catalyze, we use the Dabico, which help control the reaction and improve the final product quality. And the advantage of Dabico is this: it's low cost and low toxicity, and it's a more environmental friendly reagent. So the formulation involved the mixing of lignin, GVL, and Dabico at around 20 degrees Celsius for 15 minutes. Then we add the HDI in the same temperature and leave it stirring for around 20 minutes. And then we took the formulation rest. First it rests for an hour at 20 degrees Celsius. Then it went to an oven at 105 degrees Celsius for 10 minutes. And the last 2 hours, it was resting again in 20 degrees Celsius for the application in an automatic coater. So we tested 3 different grammage, 13.5, 16.5, and 23.5 grams per meter square. And at the end of we applied 2 layers. At the end of the application of the layers, we put it the paper with the coating. in an oven for 5 minutes and let it in the tap room with the control of humidity and temperature for at least 24 hours to start the analysis. So to understand the polyurethane properties, we did the Crafty lignin characterization. And the lignin characterization indicate a high polydispersity index, suggesting a wide range of molecular size along with high purity of this lignin. As we can see, acid insoluble lignin was around 93%, while acid soluble lignin was around 4%. Giving us around 96% of pure lignin. And although both aliphatic, when we think about the phosphorus NMR, although both aliphatic and phenolic hydroxyl groups can react with the isocyanates, aliphatic groups are more especially available. And this interaction with the isocyanate is more easy, if you can say. Since the samples showed high concentration of phenolic OH groups, the catalyst was essential to facilitate the reaction. That's why we use it to produce the polyurethane. So after we synthesize the polyurethane, we run an FTIR to evaluate if we really formed the polyurethane. So when we did the formulation, we made a control sample too. This control sample was without lignin because with DABQ in the medium, GVL can be able to react with isocyanate and form polyurethane. So to get off the interference of GVL in the formulation, we run this spectra too. And we noticed that with the FTIR spectrum, that the characteristic bands of polyurethane in both formulations were fine. So then we applied the formulation in the paper, and to evaluate the coverage of the coating, SEM was carried out, and its image shows good surface coverage and film formation. As we can see here, I don't know if you see, here we can see the film formation. And we also evaluate the paper grammage and thickness. As we expected, as we tested 3 different grammages, the grammage of each was different. And the grammage increased with the coating weight. But when we saw the thickness, we see that statistically, they didn't differ among each others. Probably because of the paper structure that we see, that it's a high porosity paper. And probably the coating was absorbed by the paper and make the thickness of them the same. So when we test the barrier properties, the first we tested the air resistance, the air permeance by Gurley method, and we see that the high porosity of the paper, but this paper is the results are comparable with reported in the literature for the type of paper we use it. It was a recycled liner board paper, And the results showed 33 seconds through the Curly method. And we can see that the barrier performance tests show that air resistance increased with the coating grammage, indicating reduced paper porosity, what prevents the oxidation of sensitive products, reduces loss of aroma and freshness when we think about food and either cosmetics, it can improve product shelf life, contributes to microbiologic protection. And this property is essential for pharmaceutical and electronic products because of the oxidation that they can have, and ensure high quality and stability of the final product. We evaluated the water vapor transmission too, and it was the same trend of the air resistance. The water vapor transmission demonstrated the effective moisture barrier, the coating application, demonstrating effective moisture bearing performance. What is good for hygroscopic products, preventing moisture absorption and reducing degradation caused by water. This property, we can see that not only protect the product inside the package, but it's good for the package resistance too. And we performed the cold test. We performed it in 30 minutes. And we have increase of the water barrier by applying the coating in the paper. And the values reached lowest of 6 grams per meters square. Ensure resistance to humid environments and protection against liquid penetration, what is important for transport and use of the packaging and the products inside it. So this property, water vapor, water absorption, the same as water vapor transmission, ensures the packaging durability and protection of its content. And finally, kit test for oil and grease was performed to evaluate the nonpolar substance barrier. And the barrier was also effective, especially with higher coating grammage, helping protect both of the coatings and the packaging itself from degradation. This test, we evaluated 12 different oils, and with the higher grammage, we achieved the 11, the test 11, that it's a good property. When we see in the literature, when we have between 6 and 12, we have excellent barrier, oil barrier properties for the paper. So in addition to barrier properties, to ensure the viability of the coating papers, we evaluated the mechanical performance. We evaluated it in burst index, RCT, that is the ring crush test, and tensile index. And we can see that when we saw only RCT and tensile index, there is a tendency to the strength of the paper grow with the high weight of coating applied. But when we see the burst index, we saw that with the high coating applied, we had a decrease in the property. Probably this is because of the penetration of the coating in the paper. and this penetration could cause the weak of fiber bond and make this property lower than we expected. And this is confirmed when we see the tensile index on CD direction. Because in this direction, the strength is more influenced by the fiber bonding. So we also conduct a biodegradability test under controlled temperature and humidity in organic compost for 6 weeks. And mass loss was observed weekly. And we have the SEM images of the end of this period. And at the end, we have 37% of mass loss for the coated paper. We select the coating 23.5, that is the highest that we tested to perform this test, because we think with the higher grammage we have more realistic results. And when we saw the paper without the liner board, without the coating, we saw a degradation of, we have a mass loss of 52%. And the SEM image...
Dr. Figueredo, try to wrap up. Thank you.
Okay. And we see that the surface of the paper coated was degraded, indicating that the polymer, the coating that we applied is degrading with in this environment. So both biodegradability and repulpability were evaluated using sample with the highest coating grammage to simulate a more demanding barrier condition. To perform the repulpability test, coated and uncoated paper samples were repulped in water around 50 degrees Celsius. And under these conditions, only 72% of the fiber was recovered by the coated samples, while the uncoated sample, 99% was recovered. And when we test this recovered fibers, we had the tensile index of the paper that was coated lower than the uncoated paper, suggesting that probably pieces of the coating was in the paper and turned the fiber bonding weak. So in conclusion, the polyurethane synthesis was successful. The application of these materials as a paper coating resulting in effective barrier properties without significantly compromising mechanical performance. And the choice of coating grammage should consider the most relevant end-use property. For instance, if burst resistance is essential, intermediate coating levels is recommended, as it still provides barrier properties. And while both biodegradability and repulpability show potential, further optimization and probably other approach is needed to increase the performance of this analysis. I would like to thank you, Professors Dr. Fernando, Dr. Leres, and Dr. Redmond, and Dr. Biliana, who supervised this research, as well as the collaborators from the respective laboratories for their technical support in many analyses. And I'm also grateful for the labs and the institutions that provide the infrastructure for this study, and the Brazilian funding agencies for supporting the project. Here are my LinkedIn profile and email address. Feel free to contact me if you have any questions, and thank you for your attention.
Thank you, Dr. Figueiredo. And now we move on to the next presentation from our postdoctoral candidate at SUNY SF, Dr. GRO. She will be talking about lignin incorporation in polystyrene. Thank you.
Good morning, everyone. I'm delighted to be here at this MDPI Polymer webinar. Thanks for the nice introduction. Today, I'll sharing my recent research topic about the synthesis of lignin polystyrene copolymer from the forest residues, a case study with ponderosa pine. Let me briefly begin with the polystyrene. So polystyrene is widely used synthetic polymer appreciated by its low cost, good balance of toughness and rigidity, and their transparency. However, the origin of this petroleum-based material makes it non-renewable and environmentally unsustainable in the long term. How about renewable resource? Renewable feedstock derived from the biomass can offer sustainable alternatives. We can use bio-derived resource such as starch, cellulose, and lignin, chitin, and among them, lignin stands out. Lignin is one of the significant renewable feedstock, which is biocompatible and environmentally friendly. Then how we can get this abundant biomass feedstock for lignin? In the US, the USDA conducts forest thinning to prevent large-scale wildfires. Ponderosa pine is often targeted in these operations, and these activities generate significant wood residues, which are often discarded or burned. Rather than treating this material as a waste, we propose using this waste residues as a renewable feedstock. And by extracting lignin from these ponderosa pine residues, we can convert these lignin bioproducts into value-added materials for sustainable polymer production. As Dr. Bunjanovic introduced about the pretreatment method to extract the lignin, there are many effective ways to extract the lignin from the plant cell wall, and there are many alcohols has been introduced to extract the lignin from the biomass. So we can use ethanol, methanol, glycerol, ethylene glycol, and butanediol, and we using the butanediol as a biomass pretreatment is very effective to prevent the condensation of lignin, and it means that this extracted lignin preserve the structure of lignin well compared to the other pretreatment method. And we extracted lignin from the biomass resource and how we can utilize it. So we can modify the lignin, and there are many researchers try to introduce the functional groups in the lignin structure to modify the lignin molecules. And lignin has two types of hydroxyl group. They have aliphatic hydroxyl group and phenolic hydroxyl group. And people try to replace this hydroxyl group part in this other functional group. And to exchange this hydroxyl group into the other functional group, the aliphatic hydroxyl group and phenolic hydroxyl group composition is important. And we also, the pretreatment, biomass pretreatment determine these functional groups of lignin structure. So in this study, our motivation and purpose is to replace the petroleum-based polystyrene into lignin material. So we use this hydroxyl group modification for the radical polymerization. So we have the hydroxyl group in this lignin structure, and by introducing the vinyl benzene group into this hydroxyl group, we can use this functional group as a radical polymerization resource, which is similar to the styrene structure into the lignin. So modification of this lignin makes to the radical polymerization with styrene together, so we can make lignin styrene copolymer. In detail, there are 2 steps divided in this polymer process. Step 1 is the lignin modification. So we use nucleophilic substitution of phenolic hydroxyl group with vinyl benzene group in lignin structure. And to use the ponderosapine-derived lignin resource, we selected 1,4-butanediol biomass pretreatment for the lignin production. And we also compared the industrial level of craft lignin together to see how the difference between the industrial level of lignin production and the BDO lignin properties. And we use VVC, which is very similar to the structure of styrene, and we modified the lignin, and it called esterified lignin. And once we prepare the modified lignin, esterified lignin, using this esterified lignin, we use styrene and initiator and prepare the copolymer. This process is the radical polymerization, and we newly introduced the solvent into the polymerization to dissolve this produced esterified lignin during the process. So the purpose of this study is that to see that the lignin modification for the radical polymerization copolymer production with the styrene structure together, and to see how it is successfully modified and introduced in the polymer system. First of all, we produce lignin using ponderosapine and BDO lignin BDO process, and we firstly mechanically refine the ponderosapine, and then using butanediol and water mixture, we reacted in a power reactor at 220 degrees Celsius for 2 hours and extract the lignin. And we used BDO extracted lignin, washed and freeze-dried in this like this figure on the slides. And before we begin to the modification, we want to see the characteristics of low lignin, of craft lignin and BDO lignin we produced. The purity shows that the craft lignin showed around 94%, and BDO lignin showed around 99% of purity. How about the molecular weight? Molecular weight was quite similar between craft lignin and BDO lignin, was 4,000 gram per mole for each, both of craft and BDO lignin. However, interestingly, the BDO process has the esterification, BDO esterification during the biomass pretreatment. So there are some esterification, 35% of esterification showed up in BDO lignin structure. And also we wanted to see how much hydroxyl group can be replaced into the esterification. So the hydroxyl group measurement shows that some of aliphatic and phenolic hydroxyl group content shows that quite similar between craft and BDO. 6.1 millimole per gram for craft lignin and 7 millimole per gram for BDO lignin. And the thermal properties is also important for the further process of the polymerization. So we measured the glass transition temperature, and the craft lignin showed 142 degrees Celsius, and BDO lignin showed lower glass transition temperature, showed at 85 degrees Celsius. And we modified esterified the lignin for both craft lignin and BDO lignin. And there is two types of hydroxyl group contents for the aliphatic hydroxyl group contents and phenolic hydroxyl group contents. And interestingly, for both types of lignin, the phenolic hydroxyl group contents significantly decreased over 95% for both of the lignin after the modification. However, the aliphatic hydroxyl group decreased, but not significant as the phenolic hydroxyl group contents after the modification. So we want to see how it is, why it is different. And we measure the 2D-HSQC NMR to see the chemical structure of modified lignin and low lignin. And as we mentioned before, the video esterification show off for the video lignin compared to the cropped lignin. And after the modification, we observed that new peaks show off related to methylene group part. But the lignin structure we use is large size of molecular weight, and it's hard to define which part is exactly modified. So we used model compound to confirm this PVC esterification. So we used two types of model compound, which one has beta-4 linkage and phenolic hydroxyl group for both, which called G-beta-G. And the other one called MG-methyl-guaiacol is only phenolic hydroxyl group incorporated model compound structure. So we used both of the model compounds and got through the same process for the modification using BBC. And when we measure the 2D-HSQC for this model compound, we observed that for both types of model compound shows methylene group, like as shown up the video lignin and cropped lignin showed up. It means that during the modification, new methylene group is generated by connecting from the BBC structure to the phenolic hydroxyl groups of lignin. And we want to see how the molecular weight distribution changed after the modification. So after the modification, the molecular weight was increased for both types of lignin. And this can be, this result indicates that the additional functional group VBC structure was attached on the successfully modified on the lignin structure. And move on to the next step, we can do the copolymerization using this modified lignin. But one of the challenges to use the modified lignin into the polymerization system is that the modified lignin is hard to dissolve in the styrene as a liquid state. So we used different types of solvent to dissolve the modified lignin. We used three types of solvent: DMSO, acetone, and THF, and 0.1 gram of lignin was dissolved in 1 ml of each solvent, and we added styrene and initiator, and radical polymerization was conducted at the given temperature and degrees Celsius. And after the polymerization, we considered the efficient solvent remover from the polystyrene, and we selected acetone for the further study. So now we have the solvent system for the polymerization, and we observed the structure of prepared polymer. However, the sum of polymer has a large size distribution, and they have no pore structure when we observed SEM image. So we added twice volume of acetone to improve the copolymerization system better. And we observed that the higher better porosity of LPS copolymer observed once we increase the volume of solvent for the lignin dissolution. And this result indicates that the homogeneous copolymerization was successfully conducted with the higher volume of lignin solvent. So we use Kraft lignin to set up all this polymerization system, and we applied BDO lignin in this polymerization. And all LPS copolymer showed even size distribution, and we successfully applied the modified lignin around 15% in the copolymer structure. To compare each of the polymer we produced, so we prepared polystyrene, which doesn't have any lignin material in the polymer system, just styrene to the polystyrene. And we used both compared Kraft lignin and BDO lignin around 10% of concentration of modified lignin. So start from the structure to identify the structure of polymer. We measure the FTIR, and styrene has the vinyl group in their structure. And once the copolymerization initiated, those vinyl group disappear. So as we can see, the wave number 1600 area, we can see that the copolymerized structure disappeared, this vinyl group bending. And also, once the polymerization started, there are some methylene group and methyl group shows generated once they are prepared the copolymer. So we can see the additional peak showed up in the polystyrene, Kraft LPS, and BDO LPS copolymer. Then how we can see that the lignin is introduced into the polymer system. So there are two assignment for the methoxyl group, the CO bond in methoxyl group, and CC bond in the aromatic ring structure. And the aromatic ring structure showed up as a shorter peak at 1500 wave number, and the CO stretching vibration derived from methoxyl group was shown up at 1000 wave number area. So we can say that the modified lignin was successfully copolymerized in the LPS polymer system. So the thermal properties is very important for the polymer material. So we measured the thermal stability of LPS copolymer. The polystyrene showed 360 degrees Celsius, and once we introduced lignin into the LPS copolymer system, both of the LPS, BDO, and Kraft increased so that the BDO LPS showed 368 degrees Celsius, Kraft lignin 370 degrees Celsius. It also shows that the maximum degradation temperature also shows that the incorporation of lignin improved the thermal stability of polymer system rather than the polystyrene itself. And we also measure the glass transition temperature of each polymer, because the glass transition temperature plays an important role when we process the polymer for the commercialized material. So we measure the glass transition temperature, and the polystyrene showed 92 degrees Celsius, and Kraft LPS copolymer showed 99 degrees Celsius, which is a little bit higher than the polystyrene. And interestingly, the BDO LPS showed 84 degrees Celsius, which was the lowest glass transition temperature among these three types of polymer. And we found these thermal properties derived from the original low lignin thermal properties. So as we can see the table in this slide, the glass transition temperature of craft lignin was 142 degrees Celsius, and video lignin showed lower glass transition temperature than the craft lignin at 85 degrees Celsius. This result indicates that even after we modify the lignin structure, still the low materials, the thermal properties is very important for the final products thermal properties of LPS copolymer. So conclude this presentation, lignin from the video pretreatment showed very high purity over 99% and has relatively low glass transition temperature than the craft lignin. And esterified lignin structure was confirmed by the reduced hydroxyl group contents and generated methylene group peak assignment through the HSQC. And once we prepare the copolymer, the FTIR confirmed the absence of the vinyl group in LPS, indicating the radical polymerization of esterified lignin and from the styrene structure together. In thermal properties of copolymer, the introduction of lignin into the polymer system enhanced the thermal stability, and the glass transition temperature depends on the low lignin thermal properties. So overall, this esterification of lignin facilitate the radical polymerization with styrene. We successfully modified and copolymerized, and which is potentially allowing an alternation of petroleum resources in material application in many ways. This project was supported by USDA. And thank you for listening, and I'll happy to have any question.
Thank you all speakers. And now we move on in this little time we have to our Q&A session. There is a question for our speaker, Gia, on polystyrene lignin copolymer. Is there any importance of drying method for lignin during the modification? For example, if supercritical drying were used, could it be more efficient than freeze drying?
Is it about the lignin production from the biomass pretreatment?
It is about the step after you get lignin into the vinyl benzyl chloride esterification. When you are drying that lignin modified, esterified, you have used freeze drying. The question is, would it be more efficient to do supercritical drying?
So for the modification, we exchange the hydroxyl group part to vinyl benzyl group, and once we washing step by step, it's quite dried very well. So we used vacuum oven dry to dry the modified lignin instead of freeze dryer or other method. So, and also those drying method works for the room temperature method. So it's quite effective way to dry the modified lignin, I guess.
In other words, your choice of solvent, low boiling point solvent acetone, after washing with ethanol,
Yeah, we use ethanol to
also relatively low boiling point. You have not used freeze drying, but vacuum oven drying, and you haven't considered supercritical drying. Is that how I understand your answer?
So we only applied vacuum oven and room temperature drying, so we didn't consider other drying method yet.
Also, question for you. Did you have more challenges during the analysis of Kraft or of BDO lignin? Would you say that they were similar to work with?
Both of the lignin types of copolymer was quite similar for the analysis. For the FTIR thermal properties were all have the same size and
Performance. The question is more about your starting lignin, Kraft lignin, which is conventional, most abundant, and BDO lignin as a novel lignin. How these two compare with each other?
so this BDO lignin was selected to preserve the more hydroxyl group contents and structure of lignin itself rather than the Kraft lignin modification and condensation. So our research design was to preserve the lignin structure better than the other biomass pretreatment, but the copolymerization system shows that the polymer properties, the thermal properties is derived from the thermal properties of low lignin. So the better selection of the lignin option is that to see the thermal properties of lignin, and our BDO lignin showed lower glass transition temperature than the Kraft lignin. So this lignin process is quite well matched for the copolymerization system.
Thank you. I would add to this response in regard to characterization of Kraft lignin in comparison, or of BDO lignin in comparison to Kraft. There are certain features which can be seen in HSQC, 2D NMR HSQC, which confirm esterification of lignin, which helps with glass transition temperature. In that sense, 2D HSQC shows important advantage in regard to structural characterization compared to, for example, regular FTIR. But what would be important to say is that BDO esterification introduce one more hydroxyl group because it is a diol alcohol, BDO, that adds into aliphatic groups. And for that, specific hydroxyl group, ROH, primary from BDO, we have to combine P31 NMR and quantitative carbon NMR to distinguish between primary and secondary. And we showed, this is the work we did not show, but in other studies, we showed that indeed BDO got incorporated into lignin, which shows in increase of primary hydroxyl group specifically from BDO. So to answer your question, yes, there are certain differences, but not really challenges, but certain things which should be taken into consideration when comparing Kraft and BDO lignin. Thank you. Are there any other questions? At this time, actually, we should wrap up. It is already 9:30 Central Time Zone. I would ask our kind organizer of this seminar to wrap up. Or should I do that at this time? Please consider submission of your work on lignin-based polymers into our special issue. And thank you so much for attending this seminar. If you have any questions, we would be happy to respond by email. Thank you.
Thank you very much, Professor Biliana. And also thank you for our speakers for the very nice presentations. And thank you for everybody that attended today's webinar on lignin-based polymers. As a reminder, I just want to mention that the recording of the webinar will be made available as soon as possible on the website of CForum. And also, if you need your certificate of attendance, you can access your dashboard on cforum.net. It can be found under my certificates. So thank you everybody for today and have a nice day.